Hi everyone, welcome to our third unit of the Foundations module. My name is Josh Edelman, and I'm going to be walking you through descriptive analysis in this video. As a reminder, this unit is the third of four which aim to walk you through the project development process. We kicked off the process with data discovery, which helped us become more familiar with our data and recognize noteworthy patterns for further investigation. Then we built off of that in introducing the concept of the analytic frame, which represents the foundational data set on which we begin our research analysis. Now, to start the analysis and communication part of this course, we will once again consider a research question or topic, this time in the context of the tables and measures we plan to develop. At its core, the goal of descriptive analysis is to provide a clear and concise summary of the data, enabling researchers, analysts, and decision makers to gain a better understanding of a dataset structure, the attributes, and overall trends. A descriptive analysis does not make inferences or draw conclusions about causality. It conveys insights from the data and leaves it at that. Descriptive analysis can be presented in many different forms, such as through aggregated, summary, statistics, tables, charts, graphs, or frequency distributions, and is a crucial step in the data analysis process. Sometimes the insights generated from a descriptive analysis may serve as the foundation for more advanced analysis, such as a subsequent investigation into establishing causality. As with the previous steps, a descriptive analysis can be quite iterative, as each finding may not necessarily signal the end of the project, but rather bring about more questions to consider. Much of the groundwork for your descriptive analysis has already been established during project scoping and development. At this point, your focus is primarily on addressing your research question. To achieve this, you can start by envisioning the final table containing your desired output. Then you can reverse engineer the steps necessary to transform your data as it stands in the analytic frame into that format. In essence, when constructing your analysis plan, starting at the end and working backward can be an invaluable approach. Envisioning your final output clarifies your objectives and guides you through the steps needed to achieve them. By following this reverse engineering process, you can conduct a focused and effective data analysis that directly addresses your research question and yields meaningful insights. Now that we have a plan in place, what does the process of descriptive analysis actually look like? We can execute our analytic plan by using the same fundamental data operations we introduced in the previous units to create our final output. Take the example in the notebooks where we want to show unemployment rates by regions over time using the Laos data. To get to the final output, there are a few steps we'll need to take. We did this in the analytic frame, but first we'll need to select the correct state for analysis. Are you interested in a particular state or region? Once we identify the specific regions, such as state or county, we'll then need to identify a granularity of time, such as month, year, or a combination of these for which you can want to calculate the average unemployment rate. Some other questions we may consider are you looking for states with the highest or lowest unemployment rates? Or are you focusing on a specific time period? Once we have answered some of these questions, then we can use data filtering techniques to isolate the data for the desired state or states or other relevant attributes. Basically, to get to the core of these results, we should ask ourselves what the story is that we are trying to tell. This story will guide the results we want to see and ultimately show. Let's consider the Kentucky WorkR dashboard as an example. This dashboard displays unemployment rates in regions within Kentucky. To arrive at these final visuals, they began with raw data and underwent a series of steps to aggregate and transform the underlying data structure to allow for this visualization. But consequently, every cell within this graph or table signifies a compiled statistic extracted from the original raw data. This work isn't complete, though, once you've generated your final output. There's still the crucial step of interpreting the results and scrutinizing the analysis for any gaps or oversights. This phase embodies the iterative aspect of the process, where refinement and further findings can be added. This is where the real art of descriptive analysis comes in. While the code necessary to obtain your results might appear straightforward, comprehending the implications of those results may not be. To begin interpreting your results, it is helpful to ask yourself about the story is behind your descriptive output. You might have several initial ideas of what could possibly explain the trends or patterns that you see in your analysis. Well-executed descriptive analysis is often not about knowing which of these stories is true, but instead what your data can and cannot tell you. Consider the Kentucky visual from the previous slide. There are certain aspects it does not convey. Notable absence is our inability to assert causality solely based on a single unemployment data source. While observing an uptick in unemployment rates within a specific region or county, we may think that it stems from significant layoffs by a prominent local company. Nevertheless, we lack comprehensive evidence to state this assertion without absolute certainty. Remember, descriptive analysis is not causal. It cannot usually tell you why something is true, but only that it is. As a data analyst, it is up to you to try and explain these results, present potential hypotheses, and also to always distinguish between what is coming from the data and what is your speculation. This is an essential aspect of data literacy, and one we will cover again and again in this course. Only when you take the full context of the data and your analysis into account can you find both satisfactory and responsible answers to your research question. So as we discussed in the past, SQL proves invaluable in accessing and investigating raw data, a necessary first step in the product development process. Additionally, SQL excels in the realm of merging and filtering diverse data sources to create an analytic frame. However, when it comes to tasks that demand a more comprehensive analysis and the creation, visualization, and dissemination of results, SQL is not always sufficient. For these purposes, alternative tools such as R, Stata, Python, or even Excel will likely prove more suitable, contingent on your specific requirements, of course. In particular, R offers a vast array of statistical functions that allow you to calculate various descriptive statistics like mean, median, standard deviation, and more with 1 or 2 lines of code. R also provides rich data visualization libraries, enabling you to create a wide range of plots and charts to explore your data effectively. And R can easily integrate with other data science tools and libraries and also databases if you need to combine different tools for various aspects of your analysis. And yes, you can write SQL code in R. So once you've come up with your interesting story for your results, what's next? How can we communicate this story to policymakers or other interested audiences? In some cases, this may be as simple as just sharing a table created through your descriptive analysis. But in many cases, a data visualization is an even more effective way to convey your insights as they relate to your research questions and make your findings more accessible to a wider range of audiences. Creating these data visualizations will be the topic of our next unit.